So yesterday we dug in a little bit to the idea of the written electron configuration and of using the periodic table to figure out what the electron configuration of any element is. So we talked about how we have essentially 4 parts to the periodic table. We've got the S block, groups 1 and 2. We've got the P block, groups 13 to 18, except for helium, which really belongs in the S block. We've got the D block, the transition metals, and we've got the F block, which is the lanthanide and actinide series. And we talked about how you can think of the electron configuration as also the address on the periodic table and vice versa. So we talked about looking at an element and finding its electron configuration by just starting at the top left and reading it like a book, knowing what the orbitals are that are this and the sublevels are that are being filled in each case. So we started with looking at sulfur. Sorry, I had to think about it for a second. And we looked at drawing that configuration out as 1s, with the 1s, the first energy level, the S sublevel, it contains 2 electrons. Then we move to the 2s, the 2p. The P sublevel contains 6. This P sublevel is full. We went on to the 3s and then the 3p, and we make sure not to make the mistake of putting the maximum number of electrons in the last sublevel, but rather the number of electrons that are there for that element. So this element only has 4 electrons in the 3p sublevel, so we would make that 4. It's a common mistake to just make it 3p6 because you're like, oh, p has 6. But all the other ones were full. This one only has 4. And we did the same thing down here. And so the written electron configuration, each term is going to have the primary quantum number, which is the same as the period, the energy level, the sublevel, SPD or F, and then as written as kind of an exponent, the number of electrons in that sublevel. So we're not actually looking at individual orbitals. You can write these out, so I could write 2px2, 2py2, 2pz2, and do it with every individual orbital within the p sublevel or the d sublevel, but that would be silly, so we're not going to do that. Yeah, so we talked about that. So looking now just in your packet on the next section, this is just showing the same idea here. Main energy level, sublevel, how many electrons are in that sublevel. And we just repeat that for as many sublevels as we have electrons in for that element. Sometimes when we get into something like this, so that's very long, we want to shorten it. We don't want to have to write out every little thing. Like if you're writing the electron configuration for radon, you don't want to be writing for 3 days before you finally get to the end. Okay, so there is a shortcut that we call the condensed electron configuration. It's also known as, or sometimes called the noble gas configuration. If you are asked a question about this on a test question, it will use the term condensed. So know the term condensed, but recognize that it's talking about the noble gases. And what it's basically doing is saying, all right, if you're, wherever you are on the table, your previous energy level has been filled, or the previous row on the periodic table is full, because you've moved on to the next row, the next period. So what we can do is say, all right, whatever the last noble gas was before your element, the last group 18 member before your element of interest, we can just take this whole configuration and set it equal to that. Okay? So you take the last noble gas before your element, you write its symbol in square brackets, got to be square brackets, and then you can move on from there. Okay? You can go, once we're basically saying the configuration all the way through krypton, and then you're going to add more stuff for whatever the element is of interest. Okay? So you will sometimes see, I'll show you some examples in a second. You will sometimes see questions that ask specifically for either the full electron configuration or the condensed electron configuration. If it doesn't specify, you can write either one. Okay? So if it doesn't say full or condensed, you can pick whichever one you want. Okay, so if we look at, I think the next page, there's some chances to do some practice work. I'm just going to go through a few of these, and then I will let you do independent practice and check your answers, okay? So let's, and you can see, sorry, I put it up here. This is on the bottom of the previous page. If you look at rubidium, we can draw out this entire electron configuration for rubidium that ends at 5s1, because rubidium is in period 5, group 1, okay? Or we can take everything up through krypton as a given, and then just add the bit that isn't included. Okay? So this is much easier to write as an electron configuration for rubidium with just the condensed noble gas notation. It's not always faster if we look at the smaller elements. So if we look at lithium on the exercises, our full electron configuration, we can see lithium's right here, so it's 1s with 2, and then 2s with 1. So that's the full electron configuration for lithium, right? The condensed electron configuration actually takes longer to write. So we would look at the noble gas that comes before lithium, which is helium, and we would write He in brackets, and then add the 2s1 because that's not included in helium, right? So that's not really any shorter. So we usually only use the condensed version when we're looking at bigger elements like rubidium, okay? Let's see. Let's do gallium. It's not on your regular electron configuration, so I'm just gonna write it up here. So let me pull up p-table real quick. So gallium is here, number 31. So we're going to have 31 electrons. It is in the p block. It is in the first column of the p block. So if we think about what its signature is going to be, it's in period 4. So the p block starts at 2. And so this is going to be 4p1 is going to be the last term. For the main group elements, not the transition metals or post-transition metals, you could actually just do that last term, and it would tell you what element it is. Okay, but we don't do that because there are so many elements for which it's a little bit dicey to do. Okay, we'll talk about some examples of those. So we're going up to 4p1. So we start at the top, 1s, 1s2, 2s2, 2p6, 3s2, 3p6, I'll write this all out in a second, 4s2, and now here's where, if you're using the periodic table method, you have to remember that the D block starts at 3, right? So it's 1, 2, 3, 4. So this is going to be 3D, and we go all the way through it, so it's 3D10, because that's the maximum, and then 4p1. Okay? So let's write that out. So for gallium, we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p1. Yes? That's what we're about to do. Yep. It's a great question. You can, just a reminder, if your D term is not the last term, you can scoot it over so that you put all the D's together, or all the 3's together, so 3s2, 3p6, 3d10, and then 4s2, if you want to. I just do it like this because I'm just following the order of the periodic table, and this is also totally acceptable. So if it bothers you that it goes 3, 4, 3, you can flip those. Okay. So if we look at where gallium is, what is the most recent noble gas? Yeah, so argon. So it's closest to krypton, but we don't have the full electron configuration of krypton because we don't have 36 electrons. We only have 31. So we have to go all the way back to argon. Okay? So that's where we're going to start our condensed electron configuration. We're going to put AR in square brackets, and then we're going to start from there. Okay? So if we're looking, we can sort of know where argon is. When you've been doing this for a while, you'll be able to kind of read through these and have a good idea even without looking at the table. But you're probably not there yet, and that is totally fine. You don't need to be. So argon is here. This is period 3 in the P block at the end, so this would be 3p6, right? So everything after the 3p6, we now have to specify. So we're done with all of this because we've turned that into that, okay? And now we just continue writing 4s2, 3d10, 4p1. Something you can, yeah.
Why would it be argon and not zinc?
And not what?
Not zinc.
Because it's the condensed electron configuration is based on the noble gases in group 18. So we only use whatever the most recent group 18 element was. It's a good question. I mean, it's sort of an arbitrary decision, but that's the convention, is to use the noble gas. Yeah, so you're going to get to whatever the last full P level was, and then turn all of that into the noble gas in brackets, and then go from there for the condensed. So much shorter. Still has the important things that you need to know that tell you where it is. Okay. Questions on that? Hey. What's up?
Can I borrow a couple inches of lab tape? Put some labels?
Oh, yeah.
Awesome. Thank you.
Sure.
Yeah, I'll bring it right back.
Sure, no problem. Okay, does anyone want me to do another one on the board? Yes? Okay. Let's pick one that's not on here. Annie, pick an element. Titanium. Okay. I'm going to just insert a page here. Okay. How many electrons does titanium have? 22. Now, we're talking about a neutral atom of titanium, right? That's what we're assuming unless we're told otherwise. So, 22 electrons. It's down in period 4, which means we're going to get through the 4s2, and then we're going to have our 3d. It's in that 3d row. So, we start 1s2, 2s2, 2p6, 3s2, 3p6. Now, I'm doing this essentially from memory because I've done a lot of these, okay? But you could also get that just from looking at the table, right? And then we go down to 4s2, and then remember again the d starts at 3, so we're going to finish, sorry I didn't make enough room, with 3d2. Okay? Does that make sense as the full? Everyone see where that's coming from? Yes.
I don't know if you explained it, but why do the transition metals have 10?
Because they have 5 orbitals in a sublevel. Oh. And so it fits 10 electrons. Yeah. And you can just count the d block, too, if you forget. Yeah. Great question. That is an excellent question. So sulfur is really freaking close to argon, right? But we don't have 18 electrons, so we can't put argon in the brackets, okay? And we can't do like argon -2, okay? So we start at neon and then go from there. So even something that's right next door, even chlorine, we're going to start at neon, okay? Great question. Okay, so here's our titanium. What is the most recent noble gas for titanium? Annie? Yeah, it's argon. Okay, so our condensed configuration is going to start with argon. Okay. That is going to take all of this and put it into that little bracket, okay? And then everything that's left over, we continue with. Okay? 23. Oh, crap. Okay. We're not going to have time to do my great idea. It's all right. We'll do it tomorrow. Okay. Let's talk about ions, because this is where things get a little bit, or can get a little bit weird. All right? So at the top of that page where you've got a little bit of space, before we get into the first row D block elements, I'm going to talk about electron configurations of ions in general, okay? So if we have a negative ion, or known as an anion, do we have fewer electrons than a neutral atom or more electrons? More. So we need to add the charge to our total number of electrons. Okay? So we take our atomic number, which we're saying is also the number of electrons for a neutral atom, and we add whatever the charge is if it's an anion. Right? If it's a cation, so we have fewer electrons, right? So we're going to subtract the charge. This is where it's really annoying that the people who figured out electrons in the first place called them negative that they've just messed things up for generations of chemistry students, because it would be so nice if, you would subtract for having more negatives, but no, it doesn't work that way, okay? So, for example, if we had oxygen, just gonna put this here. Oxygen has how many electrons? 8, okay? What's the charge on an oxygen ion? Yeah, so the charge for an oxygen ion would be -2. We would add 2 electrons to the 8, so that would be 10 electrons, right? Sodium is 11, right? What's the charge on a sodium ion? Yeah. How many electrons are we going to have for a sodium ion? 10. Yep. Right? Which is actually pretty cool, and that brings us to something that you may or may not have talked about in honors chem, which is isoelectronic species. So, O2 minus, Na1 plus. What else has 10 electrons? What's going to have 10 electrons as a neutral atom? Neon, yep. That's going to be, that's the noble gas. That's the full octet, right? So what else is going to have 10 electrons? Fluorine? With what charge? Yep. What else? What's up? Magnesium. Yep, magnesium. What charge? 2 plus. Yeah. Nitrogen, the 3 minus. Okay? These all have 10 electrons because they are all, when they form ions, they're trying to get to that full octet state. Yes? Like, how do we know what the charge is going to be? Yeah. Good question. Table that. We'll go over that tomorrow.
Is there no after-school board game club tomorrow?
Not this week.